Okay, I think we'll get started. So today we're going to talk about motion and derive the kinematic equations. Now, when we talk about motion, what we're really asking is, what is the position of the object that we're interested in as a function of time? And there could be all sorts of complicated motion. And so we hear the particle is moving up, back and forth with time and has this particular path or trajectory through space and time. Now, at any given instant, we want to know the position of that object, but there are also other physical quantities that we would like to know at this position. For example, what's its velocity? How fast is it moving? What's its acceleration? Is it accelerating? And so we want to fully characterize the motion based on the position and its various derivatives. So the rate of change of this position tells us how fast our particle is going and the direction. So that's velocity. And then we can look at the rate of change of velocity and so on. So let's just walk through the various quantities that we want to pull from any motion of an object and see the relationship to the position via the derivative. So this will involve some calculus, and if you haven't had any calculus yet, or you're just in the middle of it, we will get to the kinematic equations, which are the derived results that you can work with and solve some problems for just free motion in space. But if you've had some calculus, or maybe you're just learning about derivatives, this will be a good chance to see how that's applied here to physics. So if we take the first, as I mentioned, if we take the first derivative of position, that's velocity. But now if we look at the rate of change of velocity, so the first derivative of velocity would be the second derivative of position, and that's acceleration. We take another derivative, the first derivative of acceleration, second derivative of velocity, or first derivative, or third derivative of position, third derivative of position. That's a quantity called jerk. Now, I'm sure you've heard of position, velocity, and acceleration, and you may or may not have heard of jerk. I think the best way to think about that is, as we go down here, it's harder to get it in intuition. You know, of course, we know about position. We can understand velocity, how fast we're going, and we can feel acceleration as we're accelerating. Now, think about jerk here physically as a change in acceleration. So imagine being in a car that constantly accelerates versus one that, when it accelerates, has to shift gears. So it has to transition from, say, first gear to second gear to third gear, and you get a change in that acceleration. Well, what you're feeling on those gear shifts is jerk. Now, this is pretty much the extent of the real readily acceptable quantities that everybody knows about. But you might very well ask, well, what about the derivative of jerk, or the fourth derivative of position? Well, sort of somewhat tongue-in-cheek, those are called snap, crackle, and pop. And in the United States, there was a cereal called Rice Krispies, and the slogan was snap, crackle, pop. And so the fourth, fifth, and sixth derivative with respect to position are snap, crackle, and pop, respectively. Then another note on notation, there's this dot notation that's used, and a dot over a quantity represents the time derivative. And that's a way to save some space when books were writing, mechanics books were writing about all these derivatives that were there. It was nice to have these dots. Oh, a little mistake here. Oh no, this is right. So velocity would be the x dot, acceleration would be double dot. For example, acceleration also would be v dot. So we could, even if we're talking about velocity, we could talk about the time derivative of velocity just by putting a dot over it. So that's a notation you'll see when you read some books on mechanics. All right, well, let's work through a couple of our important examples, one being uniform motion or constant velocity, the other being uniform acceleration. And these will give us what are called the kinematic equations. And so central to the early part of any general physics course in college is to understand these kinematic equations. In the notes, I also go through constant jerk, but to do that completely generally, it's more messy than it's worth. So I do go through it with just a constant jerk from rest. But here today on the board, I'm just going to do these two. All right, so let's see how we solve this. So we're going to start with uniform motion. And so we've got v equals constant. And we can write this differential equation, as it's called, and we can separate these variables. Now this, if you're just in calculus now, your calc teacher probably would definitely not want you to do this. But this is a method called separation of variables that is very common in differential equations once you get to that course. So this is something that you can do with your derivatives. You just have to have gone through calculus so you really understand the nature of the derivative first. But we will do this. We can separate this. Then we can integrate up from the initial position to the final position and the initial time to the final time. V is a constant, so V can get pulled out. Here we have the integral of 1, so that's just going to be final minus initial. And here we have, again, V times the integral of 1, so that will be final minus initial. We can bring this initial position over to the other side, and we have the kinematic equation for constant velocity, or uniform acceleration. Or, sorry, uniform velocity. Well, with uniform acceleration, we can do a similar thing, but we take two steps. We first integrate up to velocity, and then integrate velocity up. This will look very much like this. So constant acceleration, I separate variables, and then I can integrate from V initial, not up to V final, but up to the current V. So there's a little bit of abusive notation here. We're integrating V up to some current value V between the initial and the final. And we're doing that because we're going to use it again, then we're going to integrate it again to get to the position. And A is constant, so that can get pulled out of the integral. We get V minus V initial equals AT minus AT initial. So I can solve for V by just moving this over there. And now I can come to the definition of velocity, which is the derivative of time with position with respect to time, and do our separation of variables again. But now V is not a constant like it was over here. V is this that we got from down here. Well, we integrate that up. The integral of this is going to give us a squared. We do final minus initial. So here's the t squared, or t final squared. Here's the t initial squared. So this is coming from this term. This term gives rise to these two. So it's a minus ti. This is not a variable. This is the initial time. So this is not a variable. So this will be ti, and then t with t final plugged in, and then minus ti with ti again. So this is really a ti, and that gives us the ti squared. And then we have just this constant here. So that's v initial final, and then v initial, so minus the top of the t final and t initial. Simplifying this a little bit, this is just v delta t. Now notice this here. This is plus ti squared. This is minus a half. So we're going to end up with a plus half here. This is a plus half here. And then we have this term that's here. And if we notice this and do some algebra here, this is just 1/2 a tf minus ti squared. So if we were to multiply this out, FOIL this out, we would get this. And so this here is just delta t. And so we get 1/2 a delta t squared, so the delta t squared, v initial times delta t, and then we just bring our initial position over here. And we have the final kinematic equation that we listed on the board here. And so these two equations are for two special cases: uniform motion, or constant velocity, and uniform acceleration. Again, if you've not had your calculus yet, then you can just work with these equations. If you had your calculus, then I would encourage you to try a blank sheet of paper and derive these kinematic equations. That would be a very great exercise. And then maybe even think if you can do it for a constant jerk. So try doing the derivation for a constant jerk. Again, in the notes, I've got the special case of constant jerk from a resting state.